mostly we will be talking about strengthening of metals at this point, because we're dealing with dislocations. Is there a question? Is there a question back there? Sorry. This disturbs other people. Okay, if you do have a question, let me know. So we're talking about strengthening the metals, and basically that's regarding dislocation motion. We'll talk about strengthening of polymers and sort of what you can do in terms of strengthening ceramics later on, but those aren't related to dislocation motions. So we're talking dislocation motion, and strengthening is making it harder for dislocations to move. So how do you make it harder for dislocations to move? Well, you can change your metal, and that changes the intrinsic resistance. If you change your material, intrinsic resistance, and we call the resistance to dislocation motion F. F of I is the intrinsic dislocation. So remember, F is equal to TB, right? Tau B. Okay. So that's the intrinsic resistance. That's just the bond strength. So you know that the intrinsic resistance of iron is greater than that for aluminum. All right. So that's changing the material. But within a material, what can you do? And we're going to start looking at what we will call single phase strengthening. So this means no second phase. So we're not going to be talking about precipitates or quenching and tempering of iron, carbon, and things like that. So we're talking about single phase strengthening, and there's three typical things. Something called solid solution strengthening, or sometimes called solute strengthening, grain boundary strengthening, and third is work hardening, or sometimes called strain hardening. And you all should have learned the basics of those in MSc 170. So there's chapter 7 in Callister. We've been using some of the stuff on the critical resolve, shear stress, and that. And he gave a real broad overview of those. We're going to be going into those in more detail now and understanding how they actually interact with dislocations. So basically you need to look at, one way to strengthen is to increase the obstacles to dislocation motion. Okay, plastic yielding is the movement of dislocations. That's what plastic deformation is. If you make it harder for dislocations to move, you have strengthened your material. Simple as that, but figuring out how you do that, and one way is to increase the obstacles to dislocation motion. So all of these different things, solid solution strengthening, grain boundary strengthening, and work hardening, basically make it harder for dislocations to move. So we're going to start with one, solid solution strengthening, and this is adding a different element to what we'll call the matrix element. And this can be called alloying. Okay, for example, brass is an alloy, it's copper and zinc. And you remember from Callister and probably other things, we looked at how much of one element you can add to another and have it stay a solid solution. The Hume-Rotherham rules, I think those are. Okay, maybe you've had it in another class as well. So I'm not going to go into that, but we're talking solid solution strengthening. So a single phase with randomly distributed, we'll call them an impurity for now, but you're adding it on purpose. So some people say, just call them impurities, even though they're intentionally added. So, we want to understand is how does a solute atom, so that's our impurity, the solvent is the matrix. So if you add zinc to copper, the solvent is copper, the solute is the zinc, what you're adding to it. It's like adding sugar to water, okay? So how does solute atoms interact with dislocations? And the interaction is, why are they obstacles? Why does having a solute atom in there make it harder for a dislocation to move? And there are many different ways this can occur. One is what we will call elastic interactions, and that basically means strain energy. Okay, we know that dislocations have strain energy associated with them. If you put a different atom surrounded by other atoms, it doesn't fit right. There's strain associated, a misfit strain associated with solute atoms. So you can get some interactions there, and that's what we'll be concentrating on. So that is sort of the main effect. There are other effects. Modulus mismatch. Remember, the tau is related to GB. G is the modulus of the material. If you add impurities that have a higher modulus, you're making it a little bit stiffer, and therefore your dislocation would have a higher energy. So modulus mismatch can do that. Things called stacking faults. you probably learned about stacking faults in crystallography, right? So they're going A, B, C, A, B, C, A, B, C, it goes A, B, C, A, B, A, B, A, B, C. So that example of a stacking fault. Impurities can lead to stacking faults. There can actually be some electrical interactions. So, for example, different valences can make it different how a plane slides past each other when you're moving with one atom that's got a different valence than everything around it. Can make it a little stickier or something like that. So there's just, we're not going to get into those, but those are things that can do that. And then you may have some short range order, or you could get long range order. So this would be, for example, an intermetallic, like TiAl. Okay, that has titanium and aluminum. If you get them in the right composition, they will definitely arrange in a non-random manner. It will be almost like a ceramic, like made out of two metals together. That can affect how things would slip.
Wouldn't an intermetallic make this not a single phase?
You can have a single phase intermetallic. So if it was
so
all, yeah, so it's not an intermetallic precipitate, but if you had it the right, and some intermetallics have a range of compositions where it still shows up as an intermetallic, so yes, it's not as a second phase, it's a little bit different, but that's just an example of how if the atoms do tend to segregate into an ordered fashion, as opposed to being randomly distributed, that can again affect how a dislocation would move, because you wouldn't, like once go titanium, aluminum, if you slipped it over, you'd have a titanium versus a titanium there. Things like that. But we're going to concentrate on this one, and that's the main effect, and most common. So we're going to look at just elastic interactions. So adding impurities increases yield stress, and also can be what's known as the flow stress. You know the difference between yield stress and flow stress? No, maybe. Okay. So just going back, so yield stress, I think you all know what that is, right? Is the start of significant plastic deformation. Flow stress is the stress required to continue plastic deformation. So if you're forging a material, okay, you're going to take this piece and you're going to smash it into some shape, or you're going to take a block of aluminum and turn it into a beer can. Okay, you have to draw it out. That stress required to keep the plastic deformation going is often referred to the flow stress. What do you have to do to plastically deform the material? Yield stress is where it starts. So they're both related to the stress to move dislocations. Yield stress is where it starts. The flow stress is where it continues. So if you were to look at stress, strain, okay, it comes up here, it's elastic, it starts to yield, so you would do your, say, 0.2% offset yield strength. That would be sigma yield. If you want to keep deforming this curve up here, this is your flow stress. So it depends, you know, where are you at how much strain. So your flow stress keeps going up. So often this is what we call, if you use a power law, sigma is equal to K epsilon to the n. So that's power law, and that would predict flow stress at a given strain. Obviously, if you didn't have any work hardening, your flow stress is equal to your yield stress. So if you had a material that looked like this, it went up and then just sort of basically did that. That would be sigma yield. The flow stress, there's no hardening there. So that's no hardening, and your flow stress is equal to sigma yield. Doesn't change as a function of strain. But if you have hardening, then your flow stress is a function of your strain. And that's, you know, if you went up to here and you unloaded and you came back down, you would do this. If you wanted to start deformation again, you'd have to come up and you wouldn't start. You basically have a new yield strength after a certain amount of strain. That's your flow stress. So, but anyways, we know adding impurities can increase both the yield stress and sort of the flow stress. So, again, F is the resistive force to dislocation motion. So F is going to equal F of I, just the intrinsic, plus some F of SSS, solid solution strengthening. Okay, so that's what we're trying to look at. And we know that, therefore, tau y increases by FSSS divided by the Burgers vector B. So if you look at some data, and we plot tau y, let's say it's copper, and you're adding zinc, and here is 0 to 30% zinc. We know it starts at some value here. This would be F of I over B, just the intrinsic resistance to dislocation motion of pure copper, right? That's your tau y, your tau c, or your intrinsic divided by the Burgers vector. As you increase zinc, you get an increase in tau, and typically it's something like that, and it's a parabolic increase, and tau y is proportional to c to the 1/2, where c is concentration concentration of your impurity. And you get this parabolic increase in the yield strength as you add your impurity. Why would that tend to be parabolic? Spacing of the impurity atoms varies as C to the minus 1/2. So,
Volume percent, or weight percent, or does it matter?
concentration,
Yeah.
that's a weight percent. Or it can be volume percent, doesn't matter, just it's a function of the density of what you add, right? So it can be used that. So it's actually looking at that. And so C is concentration, and actually I do have it in volume percent here. It's the number of atoms per volume. If your dislocations are a line, right? So you have a line moving through a volume. So the number of atoms that a dislocation will run into, number of impurity atoms, is going to be the number of atoms per line is what the dislocation runs into. And so therefore the number of impurity atoms per line is proportional to C to the 1/2. So that's why we get that parabolic shape, because it's the number of atoms that a dislocation runs into. So another factor that influences this is the effect of impurity in terms of how much strengthening per atom depends on the mismatch between matrix and impurity. And this mismatch is, I should say, the size mismatch. Clear on that? So we know that when you add an atom that's different than your surrounding atoms, it's got a different size. It can be bigger or it can be smaller. And if you look at that with respect to a dislocation, an edge dislocation here, so here's our edge dislocation. We know around an edge dislocation that it's tension down below it and compression above it. So here is where you're going to have regions of compression. Down here, you're going to have regions of tension. So if you add a bigger atom to a matrix, the dislocation can lower its strain energy by interacting with that and putting this bigger atom, which is in compression here, in the tension region of the dislocation. So that relieves some of the strain energy. That make sense? Because if these were smaller atoms, if these were not impurity atoms, if these were the same size here and here, there's more tension here than if you put in a bigger atom. So dislocations want to stick to these impurity atoms because they're in a lower energy state. So the amount of strain energy associated with dislocation decreases if it's around an impurity atom. Therefore, to get it to move, you have to apply more stress to break it free. Some people describe impurity atoms as like speed bumps on the dislocation plane. Yeah, I guess, because you come up to it and you have to have the energy then to go up and over. So yeah, you ran out of gas, you're pushing your car, you hit that speed bump. Okay, it's a pain. You got to push harder, right, to get it up and over that speed bump. So that increases the yield strength of the material.
Are you saying that an impurity will actually diffuse to the end of a dislocation?
It can,
Okay.
or dislocations move and hit and stick.
Okay.
So it can happen both. And there's what's called strain aging. So if you have dislocations that are stuck, you then apply a force and you break them free. Okay, then you stop your test and you know what stress that was moving at. You stop that, you let it sit, and long enough for atoms to diffuse. The impurity atom will try to get back to the dislocation, and now it actually got stronger by sitting there because the dislocations and atoms had a chance to recombine, and then you tested it again and it's gotten harder by just sitting there because some of the impurity atoms can get there. And there's things also called solute drag. How fast can a dislocation move relative to how fast can this atom try to keep up with it? So sometimes for interstitials, for carbon atoms, which can move pretty quickly, they talk about some solute drag effects and things like that. A little beyond the scope of this class, but they looked at those type of things, so that can't happen. And similarly, if you add a smaller atom, it's going to create tension. So this is a smaller impurity, tension. Where is it going to want to go? Here's our dislocation. Smaller atom to compression region of dislocation. So they go here where it's in compression, down here is tension. So that's the elastic interactions that can occur between impurity atoms and dislocations. So obviously the smaller the atom here, the more compression it will relieve up to a certain extent. So let's see. So smaller substitutional impurities move to compression, region of dislocation, larger substitutional impurities move to tension region of your dislocation, what are interstitials going to do? Remember, when you go back into your humorothery, you can figure out whether an impurity atom you add is going to be a substitutional atom, or is it going to fit into an interstitial position? Okay, so real small atoms won't substitute, they'll just fit in between the atoms. So carbon, nitrogen, oxygen, hydrogen, helium, many of those will be interstitial atoms.
Actually, I have a question. So humorothery rules, one of them is that they have to have the same type of crystal lattice.
Mm-hmm.
So what happens if you put like a loose packed type atom into, is that also interstitial or?
No, yeah, so remember the humorothery rules are to get complete solid solubility.
Mm-hmm.
So to be able to add 50% of something to something else and have it dissolve.
Mm-hmm.
If you don't satisfy all of those, you'll have limited solid solubility.
Okay.
So for example, copper and zinc,
Mm-hmm.
they're close to the same size, but they have different crystal structures.
Mm-hmm.
Copper is FCC, zinc is HCP. So you can add up to about 30% zinc to copper and it'll stay in solution. If you add more than that, you get a two-phase brass called an alpha-beta brass because it exceeded the solid solubility. So you get two phases.
Okay.
So it depends on, so if it maybe alloy, maybe you're only going to add 3 or 4% of something to it. So like in, your 4340 steels and things like that, it's iron and 1.5% chromium, 0.5% nickel, all those things can go into that. So you don't have to have complete solid solubility. We're just looking for a single phase where you haven't exceeded the solubility. So that makes sense.
Off of that, what happens if you have like a large atom next to a smaller atom next to a larger atom, all that kind of weird stuff? Because you mentioned you have like a whole bunch of different alloy elements.
You can, and that you can, they may try to get some ordering then. So that was sort of the short range order we were talking about. Yeah, it's a little bit complex. It depends on a lot of, how different are they? Do they want to interact? Are they electronegative, electropositive? So yeah, it can get really messy there. So we're looking at pretty simple things. But like with steel, nickel, chromium, manganese, they're all right close to steel, so there's not that much specific interactions. It's more of what it does to how phase transformations occur is a bigger effect. Okay, so interstitials, so small atoms. So here's our dislocation. We know up around here, compression, down here, tension. So, say these atoms are this big, and now we're going to add a small atom that is that big. Where's it going to want to fit? Right here, right? That was where, somewhere in this tension region here is where your small atoms will go. because there's more space for it to fit. So the way this works again is the solute atom has a strain field dislocations have strain fields and they interact to reduce strain energy. This makes it harder. I mean, it does say make this requires greater force to move dislocation away because it increases the strain energy. That makes sense? And anything you do to increase the energy of the system requires more stress. So if it's in a lower energy state, it's in this dip here. To get it out of that dip, you gotta apply more force than if there was no dip at all. So let's look at the effect of mismatch. Radius. So if we look at tau versus concentration, we said that there is some initial thing. So let's look at copper. It has an atomic radius of 0.128. We look at aluminum. It's got an atomic radius of 0.143. Zinc, 0.133. And tin, 0.151. So we're starting with a copper matrix, and we're going to add impurities. How is that going to affect our tau? So we know we have some intrinsic for pure copper, concentration 0, C increases this way. So we already looked at zinc, and we know that zinc sort of did this, right? Okay, so the mismatch between copper and zinc is the delta R there, 0.005. We look at aluminum. Aluminum's a bigger atom, and it's got more. So this would be, for example, zinc. That would be aluminum. And then if you look at tin, it's even got a greater mismatch. That's N. So for a given concentration, you can see you get a greater contribution the bigger the mismatch between the atoms.
This is called out to 30%.
It depends. You know, zinc has a 30% solubility, tin's probably maybe 5. So it's just sort of, you know, we're going to where it's still a single phase. So we're not looking at any really numerical values here saying how much it is. It's showing the relative effect of adding atoms of different size. So you can say this one is a more potent strengthener than this one because it's got a greater mismatch. Okay, so that's a little more background on solid solution strengthening. Well, let's get any questions on that. Again, it's all related to the strain energy, which we've gone back and shown how strain energy is related to the line tension and things like that. So that's why we look at those in terms of the strain energy of dislocations. Next topic, grain size. Oops, I'm going the wrong way. Nope, it's cat. I know I'm going the right way. So grain size, we know sigma yield increases as grain diameter decreases. And so you have to be careful when you say grain size, because when you think grain size, you're thinking, okay, what's the radius or diameter of your grain, right? If you talk ASTM grain size, it's inverse. You guys learned that when you did polishing? So ASTM grain size is how many grains you see through the microscope. So if you have a large ASTM grain size, it means you're seeing lots and lots and lots of grains through the microscope. So that means it's actually a smaller grain diameter. So it's a little bit, I talk grain size, I'm not talking ASTM. But you just want to make sure if you get on an industry and they're talking ASTM grain size, you know that it's inverse to the actual diameter of the grain. So just note ASTM grain size is 1 over, is proportional, I should say, not exactly this, proportional to 1 over grain diameter. But in this class, when I say grain size, I'm talking about grain diameters. And this is what we call the Hall-Petch relationship, where sigma yield is equal to sigma naught plus some factor K of the material times D to the minus 1/2. And this shows that sigma yield increases as D decreases, and D is grain diameter. And so basically he made a plot of that. Sigma yield versus D to the minus 1/2. You get some plot of that. And slope of this is K. That's sigma naught. So you can go through, measure yield strengths of different grain size materials within the same class of material and solve for your K. How effective are the grain boundaries in doing this? And that's the Hall-Petch relationship there. Okay, I think that's a good place to stop for now. We'll go through and understand, so what does that have to do with dislocations and obstacles?